All right, so today we are going to talk about cryptanalysis and talk about how statistical weaknesses can be obtained and how they can be used to capture secret key information, especially on block ciphers. So let's start with attack type. So in the beginning, I will give some definitions and see what kind of attacks that we can do. So total break, actually the thing that comes to mind first, because in this attack type, you try to recover the secret key. They call that in the block ciphers, we have a secret key. And of course, if you can capture it, this means that you can encrypt anything and decrypt anything since you know the secret key. So whole security actually depends on the fact that the secret key is kept secure. Okay. But of course, sometimes you can do something different. For instance, there's an attack type that we can call global deduction. In this scenario, you don't capture the secret key and you don't know what it is. But the attacker finds an algorithm A that is functional equivalent to either encryption with the secret key that you don't know or decryption of the secret key still with this secret key K you don't know. Okay, so you kind of find an equivalent function which allows you to encrypt and decrypt. Local deduction is the smaller version of this or a subset of this. So the attacker can generate the plain text corresponding to a previously unseen ciphertext or vice versa. So this kind of attacks also can happen. Okay. Another one, the distinguishing algorithm, and this is very, very important, and this is our starting point. Okay. In this case, the attacker can effectively distinguish between two black boxes, where these two black boxes are as follows. The first one is the block cipher with a randomly chosen key, which you don't know, or a randomly chosen permutation. So this actually raises the question. For instance, you are listening to a communication and you are capturing the output, right? Or in other words, you have a box, but it is a black box. This means that you don't know what is inside it. So you put the input and it gives you output. But it is a deterministic algorithm. So when you give the same input, it gives the same output. So question is there a randomly chosen permutation inside this box? Or is there a block cipher like AES with a 128-bit secret key, but you don't know what the secret key is? So can you determine just by looking at the inputs and the corresponding outputs? Okay. If you can do this, this means that you can distinguish that cipher from random noise. Okay. And if you can do this, you can actually also capture the secret key. And actually, in all of our attacks, our aim will be to find a distinguishing algorithm, but not for the whole block cipher, but a reduced round version of it. For instance, if for the AES is 10 round block cipher, if you can find a 9 round distinguisher for AES and a randomly chosen permutation, then you can use that distinguishing part, which is actually a statistical property that you use. You can use it to capture the round keys of the additional 10 rounds. And this way, capturing, of course, some round key bits will allow you to capture every master secret key bit at the end. So everything starts with a distinguisher. That is our motto in cryptanalysis, okay? So this is the most important part here. So whenever you analyze a cipher, actually your aim is to find a distinguishing property for a reduced version of the cipher. Of course, if you can find a distinguisher for the whole cipher, that will be fantastic, but that will also mean that we will throw it away, saying that this cipher is broken. We cannot use it in practice. Okay. So our aim is to find, of course, the distinguishing algorithm should be efficient. I mean, if you cannot use it in practice, then it doesn't make sense. So a question is, what kind of data I need or what can I do and so on. So with these attack type definitions, let's look at data types. These are the types that we can actually capture and use it in our analysis. So for cryptanalysis, attacker may need different types of data. Ciphertext only attacks are the most fantastic ones because we always said that the communication channel is insecure. So I am always capturing every ciphertext when people communicate. So just by looking at the ciphertext, if I can break the cipher, that will be fantastic. And in some scenarios, you can do it by the way. If the secret key is short or if the cipher has very, very obvious weaknesses, you can do it. Okay. But of course, in modern designs, this is very hard to do. So what you do need is what you do need is to have more information. For instance, if you know many plain text blocks and corresponding ciphertext blocks, you can use that relation and then try to attack the cipher. Okay, by attack I mean the attack types in the previous one. Like, for instance, you can either have the total break or distinguishing algorithm and so on and so forth by only using known plain text. Okay, in this scenario, you don't have any control on the plain text. For instance, you just ask for 1,000 plain text and 1,000 ciphertext, and you don't ask, you don't impose any conditions on this plain text. Okay, but in order for some attack to work, you cannot use every plain text, but those plain text must be in some special format. So this is what we call chosen plain text. So you actually say that, okay, I can break the cipher with 1 million plain text, but those plain text must be in this format. Okay. For instance, in the case of differential cryptanalysis, we will say that, okay, I don't care about the plain text, so it can be anything random, but I also need the same plain text, but 1 or 2 bits flips in those positions. So you actually choose your plain text. Okay. Third one, as you can see from top to bottom, things getting unrealistic, right? In the adaptively chosen plain text scenario, you capture some chosen plain text and corresponding ciphertext. Then you perform some operations on this data, and depending on your results, you go and ask for more chosen plain text. So this is an adaptively chosen plain text scenario. As you can see, collecting data becomes harder as we move down the list. But all of them are actually realistic because, in some scenarios, you don't have the encryption device, but sometimes you can capture the device. If you capture the device, this means that you can provide any input and observe the output. So in those scenarios, actually, all of these data types can work, right? But of course, if you can have something at the ciphertext only version, this means that you can just listen to communication and break it. Yes, actually, I explained everything, but let's read the slides again and see if I missed anything. So let's start with ciphertext only attacks. The attacker has access only to the ciphertext. Since the communication is assumed to be performed on an insecure channel, this is the most realistic scenario. To perform a ciphertext only attack, the cipher should have significant weaknesses. For example, RC4, where there are many statistical weaknesses, and also A51 stream cipher, which has short secret key and which we can use it to listen to 2G GSM communications in real time. You can really decrypt this, and actually you can create tables using time memory trade-offs. So I will explain it in detail in the future. Okay. Yeah, the second type was non-plain text attacks. It is assumed that the attacker can get n plain text and the corresponding ciphertext. Here, actually, we are thinking about blocks here because every block will give you something else. This scenario is realistic in practice because the attacker may get some blocks of the plain text, trick the key holder to encrypt a document which is known by the attacker, which Japanese did during Second World War. They gave some United States officials saying that this is a secret document, just encrypt it and send it back to the United States. But they listened to the communication. So they gave the plain text themselves and listened to the communication and obtained the ciphertext. So this way they obtain it, both of the plain text and ciphertext. But they can also capture the device to provide any plain text and store the corresponding ciphertext. Of course, this last one is valid for every attack scenario, because if you capture the device, and this actually by device, you can think actually anything that can encrypt it. For instance, all right, for instance, a mobile phone also in this scenario. At the crime scene, if you capture the mobile phone, but you cannot pass the screen, if you cannot unlock it, you can still communicate with the chip and provide plain text and ciphertext. So this way you can try to, obtain the secret key somehow. Similarly, if you buy any device that has cryptographic properties in it, think about the smart cards, PlayStations, anything that has a security chip inside. This means that you can actually provide, but since the secret key inside the device and it is, tamper-proof, you cannot open it directly, but you can, interact with it, provide input and observe the output. And also you can perform side channel attacks, which I will briefly explain in a minute. Chosen plaintext attacks, the attacker is able to request the encryption of n plaintext of their choosing and captures the corresponding ciphertext. More unrealistic compared to non-plaintext attacks. However, there are many examples in the history. And for the fourth and the final one, adaptively chosen plaintext attacks, the attacker is able to request encryptions of some plaintext, possibly seeing encryptions of some plaintext first and making some calculations using them, then ask for more. So it is adaptive depending on the result you observe. So more unrealistic, of course, compared to other ones. But again, if you have the device, you can interact with it and do this kind of attacks. So finally, let me talk about the source types. The success of an attack is measured according to the resources it uses. First and obvious one is the time or effort required to perform the attack. So if the attack is really fast, we measure it in terms of time. So for instance, you can say that, okay, on this laptop with this Intel i5 CPU with the model, it took like 13 seconds. You can say this in your paper. But if it is not that practical, you can actually measure how much effort you need by number of encryptions you are going to perform. For instance, you can say that, okay, I can break this many rounds of this cipher by performing 2 to the 90 encryptions. You obtain that value theoretically because you don't have any computational power that could afford 2 to the 90 encryptions. That is the idea. So you can either give the time in terms of seconds, minutes, years, but you can also give it as the number of reduced round encryption operations. Memory, the amount of memory or storage required to perform the attack. So this is important. During the attack process, maybe you need to keep some data in the memory, or maybe you will obtain some results, like you will use counters in differential cryptanalysis to observe how many times that statistical property is observed. So those counters has to be stored someplace. And sometimes you need to store many counters. So it might be like 2 to the 100 or something, which currently we don't have that amount of memory in our computers, right? So memory is different than data. The third one is data. This is the amount of data required to perform the attack. For instance, we talked about in the previous slide what kind of data we may need, right? Ciphertext only, non-plaintext, chosen plaintext, and so on. But here we are interested in the amount of that data. For instance, you might say that, okay, I can break this cipher, but I need 2 to the 100 chosen plaintext if it is like a differential attack. If it is a linear cryptanalysis, then you will need non-plaintext, not chosen plaintext. So your data complexity will be something like 2 to the 80, or depending on your attack, of course. I'm just randomly producing numbers here, but you will say that I need this many non-plaintext. Okay. If it is a boomerang attack, it will be adaptively chosen plaintext. Okay. So attack types actually determines what kind of data you need at the end.